name's Peter Robinson.
And I'm Adrian.to.
Yeah, so I work at Protocol Engineering Group, Pegasus, at Consensus, and I'm a researcher.
Yep, and they're the same, but I'm on the product development team helping to develop Pantheon.
Yeah, so tell us a little bit about yourself.
I actually started out in web content management way back, then some high performance, low latency Java in financial exchanges, and here I am in Ethereum, so doing some low level protocol work.
Cool.
Just love finding new challenges and really enjoying kind of getting into the Ethereum world, really understanding a lot of the different trade-offs and stuff that's there.
Fantastic. What are you going to tell us about today?
So today we're going to look at the Pantheon architecture, get a real overview of the different components that make up the system and how Ethereum node works in general, but specifically how that's represented in Pantheon as well, and kind of give you a feel of how to navigate around the code base in terms of a high level, what you're looking for in those components. And then hopefully that's a jumping off point for whatever you actually want to get into and do, whether it's contributing code or just understanding more about how it works.
Okay, that sounds fantastic. So everyone will be going live and starting the actual meetup itself in about 10 minutes, so you might want to skip forward in the video if you're watching the recording. Okay, thanks Adrian.
Not much. Not cool. Maybe you're looking to join the workforce or...
No. Oh, as long as you have to, I guess.
Yeah.
Get more done that way.
Oh, yes. Pete, how you doing?
Oh, really well.
Good to see you again?
Good to see you. Yeah. Nancy's about if you want to have a chat with her.
Oh, yeah. Didn't reply back, so, yeah.
Yeah.
Yeah, I was well.
Yeah.
It's a cool space.
Oh, Madeline, this is Lucas. Lucas Madeline. This is, I guess you could call this the original Lucas who joined at the same time as Rob.
I think we know.
We actually know each other through our children.
Yeah.
Oh, there you go.
My sister was
Well,
best friends with
yeah.
So Lucas actually worked.
Not really that big,
No, it's not, is it?
It's not the big city after all.
So Lucas worked in Pegasus about a month after I started in Pegasus, and helped when we were doing the quorum stuff. He's working on that for me.
Cool.
Cool. Cold
I
break.
still need to understand the user person task that are online.
Well, I did help build some online, so yes, I could probably. And she did say that.
I said, Rick told me, run it for the people to ask, and Sally said, well, that was before I was here.
Well, they are. There are people in there like Lucas and that who will have some idea of it. But
So,
another Lucas, we have two Lucas. There's two Lucases involved.
I saw Barry's name on the door. He's still there. Because Barry's consensus.
Yeah,
Barry's still here.
Sam's left.
Yeah.
Sam
Tom's
left.
left.
Yeah, Tom left.
Chris.
He's still
Chris is still. Yeah. Yep.
Cool. I spoke to Nick last night.
Nick Crickers.
Addison.
Addison. Ah, okay. Yep.
But he says more cap jam now, so.
What did that do? Okay.
Acquired.
Is it the same Pantheon who misapplied us the other day?
No.
No, he was reused the title.
Started with the slides.
Oh, he
With another
started
side.
with slide. I see.
Not a lot.
Still not seeing the live stream come up actually on the YouTube channel, but I guess it turns up in about 11. They said publishes in 10, so maybe it takes 10 minutes for it to actually appear there. So you've got 10 minutes to go, oh no! And stop it, delete it, or something bad.
If you're live streaming something, you decide that you actually don't want to,
Yeah, I guess.
So what's Pegasus up to? Like, I mean, you got the client out, so what's just keep doing off shit?
There's a lot more to do.
So
get it to run. Ooh.
The whole end of this thing's not actually attached.
Get it to run without falling over.
There's some of that.
Is that on the remit?
Yeah. Oh, there's someone. Yeah. And there's all sorts of privacy features at the top.
Hello, how are you, Mr. Stuff?
Oh, well. Here he is.
Well, yeah, it wouldn't be capable.
Well, see, I came to yours to work out what we did, and then I come into this one to work out what we built.
Yeah.
My goal is to eventually know what it is that I need.
Know what the hell we're doing.
Yeah, so I'm thinking, like, if I sit at the corner and ask some questions, that could work on maybe. I'll give it a go. And that will actually happens in front of us. No. The back rows are people who, I was about to say know nothing, but Greg actually presented last week, so that's a bit of a problem.
I feel like that's the speaker's corner. You're up next. Up row.
No, I'm up next.
I don't know.
Yeah.
You actually are up next.
Yeah.
But is there anyone using Pantheon? So, like, I see it on Infura, but is there any other clients that
I think there's a few people playing with it, a few people using POCs. We're doing some stuff with solutions in France.
Yeah.
And I think there's a few different people, I think PwC might be playing with it. So I think there's some people actually starting. We've got a 1.0 coming out, which is really the main. The first one was the basic, client.
Yeah.
The 1.0's got stuff like permissioning in it, IBFT 2.0, some, while not fully complete in the sense that it's not enterprise level, it's going to be a fast sync, for example, stuff like that. So there's the 1.0's coming out, ideally in about a week's time.
You switched to Rock DBS or was that right?
Been on that for a long time.
Yeah.
So was that on DBS? Oh, what's it like?
It's always been RocksDB as long as I've been here.
Yeah.
And that's
A lot of other clients use that too.
Yeah. So we got two dev teams here in Brisbane now.
Yeah. Two Pantheon teams or?
Two Pantheon teams. So one working on. So a lot of the people that came out of the original team that was here.
Yeah.
They're working on most of the enterprise type stuff like permissioning or authentication, stuff like that. And then the other team is very much around consensus, so they've been building an IBFT2 implementation. IBFT2, so it's a new version of IBFT. Sorry? IBFT, so consensus mechanisms, what's IBFT stand for again?
Istanbul.
Istanbul Advisor Team.
I said that was.
Yeah.
So we had one of our team members in that who was looking at it and found some problems with liveness and safety, I think. Proved there were some issues there. And so we designed one to address those issues.
How are you? I'm really good. Good that you made it. Yes, level 2 seems to be
Well, I think with the child in the seat and the kid in the back, because there was more room in the back, more room in the seat for the kid.
One of them did fine in that. The other did saxophone.
Okay, so small portable things.
Yes.
Actually, I remember reading an article last year about one of Australia's top shallows, and she's actually married to another top shallows in the world. So when they go places, they have a station wagon so they can fit their two shallows.
Because that's one of the things for control.
Someone brings the other one over.
I'm like, this is not going to be the measured one, which I know we have for. But anyway, but I was like, yeah, they've got like a normal size car. They're very problematic.
And also too, they're not going to be able to go to concerts and things like that.
I think a beach. No, you need a trolley or something, so the wheels are one side. You want something with proper size wheels. offers on it, on my place, and like, yeah. Only if you push it, and then won't go.
It's my thing.
So, did you
I'm just pushing it out privately for some reason. I think I've got to change the settings around again.
First thing you do is pretty.
I think it's actually starts working.
I was thinking it's happened. Our neighbour's child does company, and the only thing that could be worse would be that's it. I was going to say magpies go out in the middle of the field. Where the magpies can get to you. Because they're how great if you play them. Like up to before you can actually make a decent sound, that's what they sound like.
It's not especially easy.
Shackles is pretty cool.
I got it given for any birthday. I can't do barcodes on the because I just can't quite get it, and I never did enough practice. Back last year and now years ago, so it's cool.
There are two sections. So you join on the key. I'll show you where they are.
All right. Actually worked. Let's go. Wow. Except Brett is still talking about that. So hi everyone, thanks for coming along. If you haven't met me, my name's Adrian.to. I'm a blockchain protocol engineer at Pegasus, hence the shirt. And my day job is helping to develop Pantheon. So today I want to take you through looking at some of the architectural details of Pantheon, what are the major components, how it fits together, how it works, with the idea that you have a bit of a jumping off point if you want to go deeper into the code. You kind of know some of the concepts and areas that are there to look at, but also if you just want to understand a bit more about how an Ethereum client works and the kind of components that are involved with that and the work it has to do. A step down from the talk that Graham did last week, a fortnight ago, then you should get that out of this talk as well. It's obviously very Pantheon specific, but you will see a lot of commonality between how any client works. So before we jump into the architecture, what is Pantheon? It's a mainnet compatible enterprise ready Ethereum client, and what else do you need to know? The key parts in there really, the mainnet compatible we think is really important. While Pegasus is very focused on enterprise Ethereum, in a lot of ways we think it's a powerful idea that could do with some more resources and attention. It really is still centered around mainnet compatibility. The actual Ethereum mainnet, the public stuff that's out there and that everyone means when they talk about Ethereum, along with the public test nets and things like that go with it. Being able to work with those is really powerful, and just in terms of being a client, having a seat at the table and being able to contribute and give back to that public work, but also so that over time we can more and more bridge between the enterprise world and the actual mainnet, so you can start anchoring side chains and your private networks onto the mainnet and things like that. It's Java based. A big reason for that is because of the enterprise focus we have. Loads and loads of enterprise developers are familiar with Java, so to be able to jump into this code base and understand it, whether that's in understanding a problem or just helping to contribute, it's really powerful to have a language they know and are familiar with. And on the deployment side, enterprises tend to be quite comfortable in deploying Java and JVM-based software. They know the details of it, they know a lot of the security implications around it, they've usually got a JVM installed already and they're running some applications. So really familiar. It's open source, you can go and download it for free, you can check out the code, and I encourage you to. It's a fantastic way to actually explore and understand this in greater detail. It's a very familiar code base. A lot of the feedback we have gotten since we open source is that it's quite easy to find your way around, so don't feel like you can't just jump in and have a look around if you're at all familiar with Java. And the fact that we've used the Apache 2 license is also quite important in terms of our enterprise focus. A lot of other clients are GPL based, and the copyleft provisions in the GPL tend to scare away a lot of enterprises. So it's nice to have a client out there that's got the more permissive licensing. We're working, the enterprise ready side is targeting kind of enterprise Ethereum Alliance compatibility. They've got respect, covers some great features like permissioning and privacy and a range of other things. And some of that's in Pantheon today, some of it's to come, but we really want to flesh that out so that when you are running a private network, you have a lot of power and flexibility in there. And a lot of that kind of comes through in terms of the code base as well. It's quite flexible. I'm going to say quite a lot. We like to avoid having if statements scattered through the code. And you kind of see the details. We don't want to think if I'm in enterprise mode or if I'm in mainnet mode. We try and keep it really flexible so that it's quite agnostic and just easy to plug bits in and change things around. Supports multiple consensus algorithms, so proof of work from mainnet, but also click and IBFT. And we've got some improvements in IBFT, Adrian.to, which will be out of the 1.0 release that's next week. Next week is the aim. Big crunch time at the moment to test it all. And speaking of testing, we put a lot of time and effort into automating our testing, both in terms of the traditional unit tests you'd expect in any code base these days, but also at a much higher level in terms of acceptance tests. We won't have time to go into it today, but you'll see there's the capability for any tests to be able to spin up entire private networks, multiple nodes, get them all hooked up, fire in transactions, check the results. So we can automate a lot of that testing, and that can be really powerful, and we want to continue developing that. So, the architecture, as promised. That is basically an Ethereum client. Few key parts there, and we're going to work on this from kind of the bottom up. So we're going to start by looking at storage and how things work at that low level. We come up through chain processing, which is how we make changes to that storage and a lot of the actual kind of the stuff that's in the Ethereum yellow paper, the really consensus-specific stuff that clients all have to have the same. Through what we're calling core here, which is how we synchronize, how we work with the rest of the peers on the network. And finally, dev-P2P, which is how we actually connect to and communicate with the other nodes. Sitting on top of it all, which we won't actually talk about because it's simple from an architectural point of view, and apologies to all the developers who spent so many hours getting all the details right. Simple from an architectural point of view, but detailed in code, is JSON RPC, which is effectively an Ethereum client's user interface. Most of it is done programmatically through sending those requests, and it kind of cuts across everything because different methods within that can query the synchronizer state. They might be able to call into the EVM to execute transactions. They can work with how many peers you've got and query stuff about dev-PB, and even right down into querying stuff about what's happening in storage. So, storage. Well, we've got 4 things there. There are actually 2 that really matter. The world state archive and the blockchain. The consensus state and sync state can really be derived from that. So they're not actually stored on disk, but they're useful bits of state that we've got. But those are the 2 we want to look at. Firstly, the blockchain. It's probably worth just taking a brief moment to note that the blockchain has the history of transactions, but it's actually completely separate to the current world state. That's stored off separately. So when you want to know your account balance, you go to the world state. You don't tend to go back through the blockchain, but you can always calculate the world state by applying every transaction in order to the blockchain. So that's why there's 2 separate things there. And the blockchain has all those headers and bodies, and it's responsible for being able to index them and look up very quickly what is our canonical chain. So if I'm asking for block 100, it knows what the hash of that block is. You can go and get it for me quickly. Because in proof of work and a lot of other consensus algorithms, you don't necessarily have a single chain, you might have forks that come off. The blockchain at this state and storage level is also responsible for tracking what the canonical chain is and switching between forks and updating its indices as possible, as needed. So if we're following off down this fork, and all of a sudden we find that a separate fork is a higher total difficulty, and it's now a third fork, it'll switch. So it changes its chain head from pointing over at fork A to fork B, and goes back along and indexes all the things like the transactions. So transactions that were on this chain and aren't there now get taken out. Transactions that are here are indexed so we can look up which block they're in. Those kinds of things. The only way to modify a blockchain is by appending a new block. That's the only mutable operation it supports. And everything else is just driven off that. So a chain reorg happens when you append a block that makes this one higher total difficulty chain than the other. And it supports a single level of transaction. This is more like the database level of transaction that you kind of see everywhere, where you really just want to make sure that when you commit some data, it's either all there or not there. If you're killed off in the middle of it, you don't want half the data written. So it's all about consistent state, not so much about nested transactions. The world state is a bit different in that, and we'll get to that, but what does it store? Well, it's the actual account data, and the core of it is the account state trie. The account states contain your nonce, your balance, a hash of the code that is in that contract, and a hash of your storage root. And then your storage is actually another trie which is separate. And the code is stored separately under its hash. So there's a lot of looking up from hash to actual data as you walk through these tries. And the responsibility about world state stuff, and this is all under a creatively named class called World State Archive. It's kind of the root of this tree. It tries to encapsulate all those tries. And instead of you having to walk through the account state tries to find the account or the data you want and parsing all the RLP that's in there, it provides a nice simple interface that you can say, I want the account at this address. It'll get the data for you and give you back a nice simple interface called account, where you can just say, get me the current nonce, get me the balance. I want storage of this key, and so on. And it knows how to do all those lookups and that kind of thing. So the rest of the client can stop worrying about tries, you can stop worrying about all those details and just get to the data it needs. And in terms of the transactions, when you're applying a transaction in Ethereum, you can wind up with multiple nested levels. So I submit a transaction, the EVM's partway through executing, and it gets a call opcode, which actually basically creates another transaction and calls to another contract. That contract may roll back, it might hit an error, something happens. All the changes to the world state in that second call get discarded, but we might still keep this first level. So we can nest quite arbitrary numbers of levels of transactions. There's a limit to the number of calls in terms of the spec, but in terms of what the world state supports, arbitrary number of nested transactions, any of which you can roll back, or you can choose to commit and it folds it down into the parent and so on. And in Pantheon, all of this is backed by RocksDB, so it's key value storage, and pretty much everything is just the hash of the data to the actual data. So it works great for world state, particularly, where every node is already indexed by its hash anyway. You can just grab that back out. Same for block headers, hash to the header. Block bodies, same thing, code. There are a few special keys in terms of current chain head and some of our transaction indexes and so on that we use in there. But pretty much each time we go into the database, it's because we've got a hash and we want the real data. So taking a step up, what drives all these changes? Who's appending blocks? Why are we updating our world state? What's driving that? All of that is the chain processing logic. And this, I think, is probably the key point where I'd suggest anyone getting into Pantheon starts looking. And in particular, the protocol schedule class. So the protocol schedule and the protocol specs it contains are there to provide all the rules of how Ethereum works. Everything you can do to a blockchain, all the validation logic, all of that is bundled up in there. And the idea is that at any point in Pantheon, if you want to perform some operation, you want to import a new block, instead of having this if condition like the one here in terms of, if the block I'm importing, its number is greater than when we had the homestead fork, then I'm going to go and do homestead rules, or I'm going to act like Frontier or Furious Dragon. It should be completely oblivious to those kinds of checks. What it wants to do is goes to the protocol schedule and it just says, for this block number, get me the rulebook, get me the protocol spec that tells me all the things I can do and knows how to do it. And then it can just work with them in a completely milestone agnostic way. Importing a block just becomes, get the protocol spec, get the block importer, tell it to import the block. And it deals with the fact that block reward might have changed, or the gas cost might have changed, or all those details that happen in different Ethereum forks, as well as all the details of changing consensus algorithms. So proof of work versus click, say. Those changes are entirely encapsulated within the protocol schedule, and the rest of the client shouldn't need to care. To make it really easy and clear what the difference between each protocol spec is and what changed in each milestone, we've got a protocol spec builder class. The insides of that class are pretty horrible. Lots of dependencies and kind of managing stuff. But if you look where it's called, it comes out really nice. So this is our actual tangerine whistle definition. And what it's saying is that we want to start with the homestead definition, which is the previous milestone. And all we want to do is change the gas calculator. And we want to change the name. That's all we needed to do. Tangerine whistle was one of the emergency patches because it was an operation which had too little gas. So that's the only change that was in that spec. Really easy to see it, really easy to see, oh, there wasn't a change to block reward, there wasn't a change to transaction processing rules. The only thing was that we changed some gas costs. Really easy, really declarative. And we'll see how, towards the end, we'll talk about how click changes can be applied, and that's still fairly straightforward. So the categories of things we can do, we've got a bunch of validation, both in terms of a top-level block validator, that we can just say, hey, I've got a block, tell me if it's valid, tell me if I can import this to my chain safely. Coming down to things like header validators, a lot of this we come in at different levels at different times, so the synchronizer gets headers quite asynchronously. We can validate them ahead of time before it gets ordered and ready to import on the chain. So we can check things ahead of time and do that in a more parallel way than the very sequential one block after the other you have to do when it's on the chain. The block header is a little bit special because it's the most common place for there to be changes in a milestone change. The header validation rules change a lot, and they change quite drastically between proof of work and click and Adrian.to. So it itself has rule-based validation, and you'll see a header validation rule interface there that you can, there are a bunch of different rules. So there's proof of work validation rule, there's difficulty validation rule, parent validation rule, each checking one specific thing, and you can combine them very easily. So for click, it says I want to validate the parent and the thing the same as mainnet does, but I don't want to validate proof of work, so I don't do that. And my rules around difficulty are different, so I'll just sub in those different rules. And this is where we're starting to get a lot of flexibility. Again, it's about being able to set this up in the protocol schedule, not have it leak through the client. You won't see anywhere in Pantheon, and last time I checked this was true, you won't see, if click is in use, do this. It should be really, really simple, once you get past the initial setup, obviously. And we can get into the block body validator, and the transaction validator is used a lot for the transaction call. The other big part of this is the actions. What can we actually do? Most importantly, block importer. This is kind of the key of moving your chain forward. Really good class to look at. There are actually 2 block importer classes in the Pantheon codebase. One is the command line, I want to import some blocks. It becomes pretty obvious it's not the one you want. The other one is actually a part of the protocol spec. And it will go through validating, processing all the transactions, and then finally appending the block to the chain. And it uses kind of all of these. So the next level down is I've got a block and I want to process it. And JSON-RPC often uses this at this level as well. You can run a debug over a particular block or over a transaction without committing the results to storage, but just so that you can get those results back as part of a JSON-RPC request. So the block processor will use the transaction processor to apply each transaction. Then it does things like pay the block reward, apply any gas refunds, self-destruct accounts that have been queued up for destruction as part of that. And then the transaction processor is one level down again, where we're actually walking through the transaction. We're actually going to execute the EVM after we've validated the transaction, do all those kinds of things, deduct the upfront gas costs for the contract, and so on. And the EVM is even pluggable because often the only change in a high fork is that there's some new operations. And so we've got an operation registry and pre-compiles that are there. So that again, we can reuse that same EVM because the logic is almost identical across pretty much all the milestones, I think. And it's just which operations are available to change. Some other bits that change a lot, you'll see floating around in protocol spec, and these are really just inputs to other things. Things like the block reward, really easy to change it one line. You can just say instead of this block reward, I want that one. The gas calculator we saw for Tangerine Whistle, difficult calculations, change in the number of milestones, a lot of the time to push back the ice age. And the block hash function is an interesting one. It hasn't changed on mainnet. The rules for hashing a block are really straightforward. You take the header as RLP, you hash it, you're done. But for click and IGFT, it's actually different. You have to exclude some of the pieces because they actually do vary between different blocks people might have that are otherwise equivalent. Typically, which set of signers you have. You've got enough signers to know that you've got quorum, but you don't necessarily have the exact same set. So that's a pluggable function that the protocol spec provides as well. And as promised before, this is what it takes to convert from a hash proof of work to a click consensus algorithm. And it's actually slightly more verbose than it really needs to be, thanks to some limitations in Java generics. This function will take any mainnet milestone and switch out proof of work, put in click, but otherwise be the same. So you might have the frontier operations or Constantinople operations and so on. And all it's doing, these first two lines are header validation. So for headers and then ommas, on hash, omma validation is just slightly different to block headers, believe it or not. In click they're the same. So we replace those lots of details in there in terms of picking different sets of rules. That's quite significantly different to how it works on mainnet. Then we got sucked into re-providing the same mainnet instances of these. We didn't want to change them, but Java generics couldn't avoid it. We've got a different difficulty calculator. So the rules around click difficulty are about whether it's actually your turn to seal a block or not. It's not about the time-based thing that you have in Nethash. We set the block reward to 0, and who we pay mining benefits to. So the block reward, which is 0, so it's pretty irrelevant, but also gas costs. You do pay gas if you click, and that goes to the proposer of the block, not necessarily the person who's listed as the coin base in the header, because click co-opted that field for its validator voting. It's nice of them. So that's kind of things, the rules we've got for the chain. What's driving that as we continue to step up? Well, the primary thing driving it tends to be the synchronizer. Two parts to that. But overall, the synchronizer is responsible for getting us from whatever state we were in when we first started up, which is quite possibly back at Genesis at the very beginning, caught up to the chain, and then stay in sync. And the catching up is the chain downloader. So what it does is it's got a fairly simple loop that it just keeps going round and round on. First it looks to see who's the best peer I know about, who's got the highest total difficulty that they're broadcasting to me. From there, we try and find the common ancestor block that we both share. So remember, we might be off on 2 separate forks, and we might need to switch to follow them. So we follow the forks back to find which block we've got in common, and we can start syncing from there. Then we go out to the best peer we've got, and specifically from them, we ask for a series of headers spaced about every 200 blocks, I think it is, that we're going to use as checkpoints. So we know that even though we're about to fan out and ask for data from a whole bunch of peers who don't even claim to be on the same chain, but no real idea if they're going to give us the same data, we're going to go to them and ask for that data. Regularly, as we're syncing, we're going to have a checkpoint to tell us if the data they gave us matches what the best peer is telling us should be there. And that's really powerful because it saves us syncing 7 million blocks of mainnet and then going, oh, they were lying, throw it out and go back to the start. We want to regularly find that and be able to toss out bad peers that are telling us lies. And then we go into a pipeline and we really fan out to a whole bunch of threads. We go out to as many different peers as we can on the network, grabbing headers. Once we have the headers, we can grab the bodies of those. We validate them as we're going in parallel as much as we can. Then in order, we have to start executing the actual transactions. So for each block, we execute the transactions, append that block to the chain, and we can move on to the next one. And once we've kind of got that batch of blocks, then we go back to the start. We check, are we still talking to the best peer, or have we found someone better that we should switch our sync to? If we're still talking to the best one, we check if we need more checkpoint headers, if we've kind of gone as far as we'd asked for in that first batch, or if we've still got further to go, then we just keep going around. We go out and do the same pipeline thing, import some more blocks. Till eventually, we get caught up to the head of the chain, and then the downloader kind of pauses and just says, yeah, I'm good for now until I hear about a peer with a better block that seems to be out in the future. I'm going to sit and do nothing and let the block propagation manager take over. And the block propagation manager is actually pretty simple. It's what receives all the new block and new block hash messages from Dev.to, and it just checks, do I have this block? If yes, toss it, don't care, already got it. If not, am I in a place where I can import it? So is its parent already on my chain? Yes, great, go and import it. No, all right, now I need to send a request. I need to fill in a couple of blocks, most likely. And it also keeps our view of all of our peers' chains up to date. So each time they send us a new block, well, we can see what their height of the chain is. It tells us their total difficulty. We update all that, and that's what the synchronizer can use to help pick its best peer. And obviously, the one key job it has is to make sure things are ordered. We've got to apply block 1 before 2, before 3. The other part of our core is the transaction pool, which is fairly straightforward. It's what receives all the transaction messages, both from Dev.to, from other peers that are broadcasting transactions around the network, and from users over JSON RPC. So if you submit a transaction to any Ethereum client, it will wind up in its transaction pool. And it's responsible for validating them, first checking that we haven't just received rubbish, which is quite common from users, usually less common from peers on the network, and continually checking that these transactions can actually be applied. So has the account got enough balance, and that changes over time? Is it ready to be applied? Is the nonce the right number, or is it off in the future or in the past, so on? And it's then the source for the miner to pull transactions out as it's creating new blocks. Which brings us to the miner, which is another one of these components, and I'm sorry there's a couple of people in the room, but architecturally not very interesting. Great bit of code in terms of writing it. They've done a fantastic job and made it so simple that I'm not even going to give it a slide. It creates blocks, pulls from the transaction pool, creates new blocks, and sends them out to the network. Speaking of the network, now we're finally getting up to the thing that's almost in charge, that's really driving us, which is Dev.to. Because apart from responding to user requests on JSON RPC, our biggest thing is we've got to stay in sync with the network. We've got to help it keep up. We want to get our blocks out to them, and we want to make sure that we're in sync and up to date with all of their stuff. The starting point of that is to find out who the network is, find peers to talk to, and that's done by Dev.to peer discovery. It's a UDP-based protocol, typically on port 303. And it starts by going through a set of well-known boot nodes. So for the common networks like Mainnet, Rockston, Rinkeby, Gurley, and so on, they're usually just actually hard-coded into the client. The client knows, for that network, I go to these boot nodes, they're that stable. But if you were setting up your own network, you would specify your own boot nodes, one of the nodes in your network. That is the starting point for everyone to go to and find out, start asking for other neighbors. And it's then a recursive algorithm to find neighbors. So we go to the boot nodes and say, hey, who are some other peers you know about? And we get some responses. Then we go to a set of those peers that have been responded to and say, hey, tell me some more neighbors. And they give us some more, and we keep going until we've talked to enough nodes. We kind of get bored and stop. Once our peer table is full, then we've got a good view of the network, lots of nodes. We found kind of the what's the Kevin Bacon game, the 7 degrees of Kevin Bacon? Yeah. Someone's worked within 7 steps. It's that kind of thing. Once you've talked to enough nodes, you've got a really good view of the network. You are very likely to be connected well enough that you're going to hear about new blocks. Of course, once you've found those peers, at the discovery level, there's a short little ping-pong thing of like, are you alive? are you who you say you are? But it's pretty short and still UDP based. The next step up is to actually connect at the wire level. And the wire level is a TCP connection, still on port 30303. And it sets up a whole bunch of encryption, exchanges keys, gets things ready so that we have this reliable channel to talk to that peer. It also does a client capability exchange and negotiation process. So Dev P2P has a set of sub-protocols, or can support any number of sub-protocols, and each protocol might have different versions. So typically, clients will all support F, and at the moment, the current version is 63, and so they usually support 63 and 62. But Pantheon also supports the IDFT sub-protocol. I forget what the code we used for that was, but so when you connect to a Pantheon node, if IDFT is enabled, you'll actually get a response back saying, hey, the capabilities I have is F62, F63, and IDFT1, whatever we call it. If the other side supports those same, it'll pick the highest version. So if you support F63, then we'll wind up talking F63. If you don't support IDFT, though, we'll just drop that. And so you're working out a common set of protocols that can be discussed, which is a really powerful and important part of Dev P2P. It gives you a lot of extensibility into the Ethereum network. And beyond that, some keep alive, some compression at that level. But then the real work happens at the sub-protocol level. So the most significant of those is ETH, and that's where you get messages like these ones in terms of new block hashes, new blocks. When I said that the synchronizer goes out and gets headers, it sends an ETH get headers method message and will be returned with block headers. So that level of communication allows you to do most of the things you need to. And in terms of the architecture in Pantheon, we represent each of the sub-protocols with a protocol manager. So there's an ETH protocol manager, there's an IDFT protocol manager. And the Dev P2P layer will direct all the messages from that sub-protocol to that protocol manager, and it can then fan out. So the ETH protocol manager knows that block propagation manager is interested in new block messages. The synchronizer wants the header responses, and the transaction pool wants the transaction notification. But it gives you a nice separation between the two sub-protocols that you can see clearly. We've forked out from just all the world of Dev P2P to specifically IDFT, and then in future whatever other protocols we support. And that is a whirlwind trip up the stack of the Pantheon architecture. As I said, the only thing we didn't really cover there is JSON-RPC, which can get its fingers into most of this pie, because it's got a wide range of methods. We'll open up for some questions in a moment, but just before we do so I don't forget, I'll mention the upcoming meetups, which next week is Brett Henderson, up the back there. Next fortnight. Oh, I'm excited, I want this sooner. Brett will be talking about Ethereum 1.x. Now, this has flown under the radar in some degrees. Everyone's excited about Ethereum.to, but almost certainly landing first and probably reasonably soon is 1.x. And that's a series of proposals to try and keep our current proof of work mainnet running and giving it some more scalability, letting it handle the load, keeping it stable, while we wait for Ethereum 2, and because, particularly right now, the current Ethereum 2 proposal really doesn't get rid of the proof of work chain, it augments it, and it's kind of still there for quite a significant amount of time. So Brett's going to take us through those proposals, but there's things that are really quite important and worth knowing about. So probably the biggest and will be an interesting discussion around whether it comes in or how it comes in is the stake rate proposal. One of the big issues in Ethereum right now is that the amount of world state you have to maintain is growing and really big, and it makes it expensive to run nodes. So this proposal is about, well, what if we, instead of just saying once you pay to store, but then it's stored forever, what if we charged you per block some rent? And then if you are unable to pay your rent, we can discard that data, and you can always regenerate it from the chain. Lots of details in there. Obviously, I can see a few frowns. People going, oh, that's changing it. Yeah, exactly. It's something that will be really interesting to work through. Brett will take us through that.
Adrian will answer all the questions on that particular topic.
Yeah, there's a proof of concept on it on Pantheon actually, which is was quite interesting to go through. And there's a number of other proposals in terms of helping that scalability. So it's really worth coming along and listening to that, even if you haven't necessarily heard much about Ethereum 1.x in the past. Then March 20th is applications of blockchain. We've got Frederick Brian and Richard McKeon. So that'll be really interesting. Some real world usage of Ethereum and how it works. Always nice to hear, especially from down in the dungeon where I work, protocol level. And then April 3rd, where Jason Frame is going to take us through actually deploying and running a Pantheon node. So you get some hands-on experience of how to really use and set up an Ethereum node, but in particular Pantheon. So that's what's coming the next few weeks, the next few fortnights. Any questions? It's been a while. Yeah.
So with your peer neighbours and so on, is that sort of following what the general Ethereum node finding, discovery, and so on? Has there been any hints with regards to establishing well-connected networks, giving because of chain branching in where there's a fork, that well-connected networks are ostracising or getting the inside run better on remote nodes with regards to their proof of work coming through, but a well-connected one's got in first, or not necessarily first, but got in there.
Not that I've heard of. I've heard the concern.
Yeah.
I haven't heard much to mitigate that. I also have seen people push back on how much we should be concerned about that happening. There isn't a lot of evidence that it's a current issue.
There was also discussion that some of the key miners, the communication network between the miners, some of the key miners, had improved dramatically in recent times, and there was an open discussion about whether that was something on purpose that they had orchestrated, or whether it was just an aberration that, you know, someone put in a new optic fibre cable and suddenly the network between this big miner and that big miner suddenly improves. So obviously you can have less fork, less uncalls and everything if there's consensus more quickly.
Yeah, there was an interesting blow up recently actually, where the OMA rate had dropped and has dropped on mainnet. There are fewer OMAs than there used to be even a month or two ago. And there was a big thing of miners are collaborating. And actually it was a bug in parity that had been fixed. So when you propagate a block, actually you don't process all the transactions, then send it out. You just validate that the proof of work was done, and then send it. And parity was importing it all to its chain, which is significantly more time before it starts echoing that back out to the network. And that reduction has significantly improved the throughput of Ethereum and reduced the OMA rate.
I take it you welcome contributions to your testing and whatever?
Absolutely, yeah. Welcome all kinds of contributions. As I said, you know, it's a pretty good code base to dive into. Love to see that. And you'll find a lot of Pantheon developers hanging out on the Gitter channel. The easiest way to find that is just through GitHub. That can help you get started, point to areas where we think there's stuff missing, or if you've got particular areas to help you with finding a way around and getting started. That'd be fantastic, yeah.
I mean, I like the idea that you've got some high-level exception testing and you can basically start doing sort of test-driven development of this, you know, like
Yeah, absolutely.
write a test that breaks and see how to fix it. Off you go.
Yeah, it's incredibly powerful, and we've got a long way to go before I think our vision for where it should be is entirely realised, but it's been powerful even today. I think particularly the IDFT team have used it really well in terms of testing that the whole network will stand up and work together, which is pretty much impossible with just unit tests.
We're coming at the development from an enterprise mindset, so we have in our recruitment pipeline a QA, for example, a lead QA. So we're mindful that while it is an open source product, we're building this at an enterprise grade level, so testing is critical.
Yeah.
Good documentation is critical, you know, being able to help the community but also help people use the product. So, we've got a full-time documentation team who are writing the docs and got contributions to that.
Well, hopefully the software is just a byproduct of the documentation.
You're asking for a COBOL version, Lars?
No, you're sitting out there, aren't you, Raymond? Being in Java, there's probably no reason why I couldn't drag it onto a
Maybe .NET or
no, I'm dead serious about that.
Well, you're serious about COBOL? What's it?
Well, COBOL pays me money 3 days a fortnight.
Great, well, thank you for your time.
Yeah, thank you. So, that was absolutely fabulous, and thank you. So, everyone, we're going to be, for the next 2 meetups at least, we'll be in this room. So, yeah, when you're coming here, if you come 5 minutes early, then it'll help to navigate the lift system and get here. So anyway, it's been awesome, and thank you for coming along.
Unlike me, who've walked thoughtfully up ThoughtWorks and then realised, hey, 310 Edward, where the heck's that?
Yes.
You're not the only one.